All right, in this video, I'm going to talk about some things in Chapter 2 that you should know. A lot of this stuff is in Chapter 2. Some of the things I'm going to go a little bit more detail. So make sure that you get all these things and that they all make sense. So, okay. So first, I want to talk about some of the accomplishments of this guy, Hipparchus. Hipparchus did a couple of major things in astronomy. I'm going to talk about a couple of them here. One of them is he started the whole star brightness idea, which is called the apparent magnitude scale. Apparent because that's what they look to us, right? You can see a star just because it looks bright doesn't mean it actually is bright. Maybe it's a dim star that's close, you know? Or if it's a super bright star that's far away, both of them could be bright. But we don't know that, and he didn't know how far away the stars were. He just said, okay, that's a bright star, that's not so bright. And because he wanted to classify the stars, he made a big list. I think he classified like about 300 stars. He wanted to say how bright they were, and he gave them coordinates in the sky and saw how close they were to other stars and everything. So he tried really making a really good list of data on stars. And so he wanted to tell how bright they were. So he called the brightest ones, he called ones. And then he said, then there's twos, threes, 4, 5, 6. And he said sixes you could just barely see on the darkest night when there's no moon. You could see sixes, those are the dimmest you can see. And you know, ones were the bright stars. Again, these are just stars, not planets and stuff. And we still use that scale. We've made it more mathematical. It turns out pretty darn closely the brightest stars he saw compared to the dimmest ones are about 100 times dimmer. As far as stars go, if you compare the dimmest star you can see with your eyes, it's about 100 times less light than the brightest one you can see with your eyes. All right, in Leavenworth, on a really good night, you're lucky to see 5s. Okay, it's pretty hard to see magnitude 5s. You can on a good night. You'd have to have the best night ever to see 6s. Usually you got to go way up in the mountains with no full moon, you know, less air between you and the stars to be able to see 6s. You have to have a really, really good, they call it viewing. You have to have really good viewing to see 6s. But you can see 5s in Leavenworth. And certainly you can see 4s and 3s and 2s and stuff, okay? So they made it more mathematical since Hipparchus. Now they say they make it exactly 100. 100 times dimmer is a 6 than a 1. If you do that, it turns out that each one is about 2.5 times dimmer. If you go 2.5 times dimmer times 2.5 times 2.5 times 2.5 times 2.5, you get 100. It's really like 2.512. But it works out where that works. So every magnitude is 2.5 times dimmer. Now, once they made it more mathematical, and then they want to say, okay, what about planets? What about the sun? Then they had to go to 0 and the negatives, because if 1's the brightest, well, there's things brighter than the brightest star. Planets are brighter than stars typically. And what about the moon and the sun and stuff? So they had to go to negative numbers, okay, which is kind of unfortunate. Usually you think the bigger the number, the brighter it should be, but this scale works backwards. The bigger it is, the dimmer it is. So, oh well, it works. But negative numbers are the brightest. So now, when we look at that, and they have a table here, and this table is later on in your book, but we'll just talk about it briefly now. This is about where some of the brightest things are. The sun is like a negative 27 or so. The full moon is like negative 12 or 13. Sirius, the brightest star, Sirius is right here. It's like a negative 1.46, about negative 1.5. I had you look that up on Stellarium just to get you kind of used to those numbers. So the brightest star now is not a 1. It's a negative 1.5. Again, they redid the scale to make it more mathematical, and it just turns out that's the case. So Polaris, the North Star, and you guys look that up also, it's like a 2 point something. It's not a very bright star, but it's the only one near the north celestial pole. It's the only one that stays directly north and doesn't move as the night goes on. So it's famous, but it's not because it's very bright. It just is in a really good place. But it's reasonably bright, right? It's like it's a 2 or something. And again, the naked eye limit without a telescope, you can't see dimmer than 6. With telescopes, the bigger the telescope, the dimmer you can see. You can see 15s with a really good telescope. Okay, so that's the apparent, what it looks, brightness looks to you. The brightest planet is Venus. Venus is like a, what is Venus? It's like a negative 4.5. So I think this is supposed to be Venus here. Yeah, I just didn't scroll down far enough. That's supposed to be Venus there, negative 4.5. Yep, Venus, when it's brightest, Venus gets brighter and dimmer. So Venus is the third brightest thing in the night sky. The brightest thing in the sky. The brightest thing is the sun, then the full moon, then Venus when it's brightest. And other planets are brighter than Sirius. Jupiter and Saturn are typically brighter than Sirius also. I think Mars too, but it all depends on where they are. You know, they change their brightness. Okay, that's one thing I want to talk about, was the whole magnitude scale that Hipparchus started. The other thing that Hipparchus did was he noticed by looking at data, because he made this list of data of how bright the stars were and where they were in the sky, and he compared it to people that were before him, up to 150 years before him, people have been doing similar things, and he noticed that the position of stars was changing. That things, especially where the North Star was changing from 150 years, which is pretty good because it takes a long time to change. Now, he couldn't work it out in detail, but now we know that it changes over a 26,000 year cycle called precession. And if you're in class, I'd show you some tops and things precessing. It's kind of hard to demonstrate this without, I don't know, moving the camera. But the idea is when you spin a top, and you guys have done this before, the top goes like this, right? It doesn't fall over unless it goes really slow, but it precesses. This point here, the tip of it goes in a circle. And typically as it goes slower, it goes in a bigger circle until it falls over. But that's called precession. Things that spin, that there's also a force on here, it's a force of gravity, tend to precess. The Earth has the force of the sun on it. So the Earth is spinning once a day, right? It spins once a day as it turns around, but the sun is pulling on it, and so its north pole tends to sweep out a big circle. We're tilted 23.5 degrees relative to the ecliptic plane. We go around the sun in this flat plane called the ecliptic plane, and we're tilted 23.5 degrees to that, not straight up in the ecliptic plane. That's what gives us seasons and lots of other stuff. Makes it much more complicated to kind of figure out motions on Earth because we've got this tilt going on. And that tilt, it's always 23.5 degrees, but it sweeps in a circle at 23.5 degrees. The Earth, since it only turns once every 24 hours, it ends up taking 26,000 years to make that circle. Of course, the top might take a couple seconds. That's called precession. So Hipparchus actually discovered that. He couldn't work out the 26,000 years with the data he had, but that's what it turns out. So therefore, right now, our axis is pointing towards the North Star, star Polaris. Okay, but it's not always that way. It's going to make a big circle away from Polaris, and in 26,000 years from now, I think it's really 25,800. It's not exactly 26,000, but that's good enough. It's going to be back at Polaris. So there are times when it points to other stars. Some other ones that I think it pointed pretty close to Vega at one point. It pointed close to the star Thuban at one point. It talks about that in the book. However, never as well as our North Star. It could point to really dim stars like magnitude 6s, but you can't see them. So as far as a bright star that the Earth's axis points towards, the brightest, best one ever is right now. We have the best North Star in the history of the Earth. Never in 26,000 years does the North Pole of the Earth's axis point towards a star as well as it does right now. Okay, in about 5,000 years, there won't be a North Star. You look up where it should be, and there's just a blank part of the sky. There's no South Star right now. The South Celestial Pole. If you follow the North Pole of the Earth out into space, you'll come really close to the North Star, but there's no bright stars in the south. It's harder to find your way around there, right? You can't just find the North Star. Oh, that's north. It's a blank part of the sky. We have the best North Star that the Earth ever has. So hey, that's pretty good. We're lucky to be in this time where we have a good North Star. So hey, if you're ever down and upset about things, say, hey, at least we have a good North Star, and that's pretty good. Okay. So Hipparchus discovered that. And that's also why astrology doesn't work. because 2,000 years ago when they made up all these horoscope stuff, the Earth's axis has changed, right? 1/13 of the way around in 2,000 years. And so where something pointed, we go through all the constellations in 26,000 years. So like I said, why 2,000 years ago on February 25th, the sun was in Pisces. Well, now it's in Aquarius, and about every since there's 13 zodiac constellations, right? Ophiuchus, the one that no one talks about. Over those 13, in 26,000 years, on my birthday, the sun is going to be in each of those 13 zodiac constellations, and it'll be back to Pisces in 24,000 years. Right now it's in Aquarius, and then it's going to move on to the next one, the next one, the next one on February 25th until, again, it comes back to Pisces. So again, that's one reason why astrology doesn't work if they keep the old constellations, the old zodiac signs, because the sun moves through those. Okay, so those are some things that Hipparchus did. Let's see, I want to talk about one other thing, just basic stuff about the celestial sphere. I actually have the real celestial sphere here. Okay, pretty cool. Here's the Earth, right? The Earth's in the middle here. And we can imagine, of course, it doesn't work that way. The stars are at different distances. But this is what the Greeks imagined, and it's useful to imagine that all the stars are on this big glass, this one's plastic, on this big glass sphere stuck to it. Now the planets move. You can't put planets on this thing because they're wandering. They're the wandering stars. But if this is the way it is, and the Earth's axis is straight up, then the sun follows this orange line. Okay, if the Earth's axis is straight up. Now really we know that the Earth's axis is tilted 23.5 degrees, and the sun makes this nice line like this. Okay, and this is the sun's path. I can move the sun across the sky, and the path it makes follows that orange line. That's called the ecliptic, and it's again because the Earth is tilted at 23.5 degrees. If we're straight up and down, relative to the plane we go on, the sun is in the orange line to be around the equator. Okay, so the equator of the Earth cuts through the equator of the celestial sphere, so it's called the celestial equator. The path the sun is in, because the Earth is tilted, not really the sun, but it looks like the sun is tilted, it's 23.5 degrees up, right? It's 23.5 degrees off from that. However, it goes 23.5 degrees down and over, and right where it crosses those in the equinoxes, like right there, it crosses the celestial equator on the equinox. The ecliptic crosses the celestial equator on the equinox, and then over on the other side it does it again. And then this is called, of course, the north celestial pole, right above it here, way out there in space. Or they can't put it here because of this plasticky stuff, but the North Star should be pretty darn close to this metal thing. And in the south, there is no South Star, so they didn't have to worry about that because there's no south, there's no good decent star right there. Okay, so celestial sphere with the north celestial pole, the celestial equator, and then the south celestial pole, and then the ecliptic is the path the sun makes. And of course we know that the stars in the background, wherever the sun is, these constellations, these groups of stars are zodiac constellations. There's 13 of them. And overall, there's 88 constellations on this whole celestial sphere. They're all different sizes because they all kind of put boxes, scientists put boxes around the different shapes so they could say where to look. If I know something's an Ursa Major as I'm an astronomer, oh, I know where to look. I know the best times of the year and the best times of night to look there. So it's helpful to have constellations. Astronomers typically know them all really well. They're used to using them. Right, about half of them are down here. We can't see them because we're on the top of the Earth. So we can't see these southern ones. You got to go south to see those. But we can see the northern ones, of course, pretty well during different times of the night. Obviously, at night, some of them are up during the day. We can't see those. We see the ones up at night. Okay, so celestial sphere. The point when we're lying here, right? The point. So there's Washington somewhere in here. The point directly over your head we talked about is your zenith. At your zenith is the point directly over your head. The point directly below your feet is your nadir or nadir. If you point to a star, the altitude, the angle your arm makes with the ground is called the elevation or altitude. And then this way, the compass angle, going north-south, is called your azimuth. And it can be measured in degrees, and it can be measured in, or just say north, northeast, southwest, south of southwest. That's not as exact as degrees. Always remember with degrees, okay? Degrees, north is 0, and then it goes 90, just like it goes around this way, 180, 270, and back to 360, which is typically 0 again. So that's north, this is east, this is south, and that's west. So just keep in mind those numbers. You should know those the rest of your life. Hipparchus had nothing to do with this, so let's erase him. So north, south, east, west, and those degrees. And so like south, northwest would be like right here. And then here you'd say west of northwest. It gets confusing. It's just better to say the degrees. Now, like we mentioned before, scientists, for historical reasons, don't use decimals for degrees when they're talking about latitude, when they're talking about star coordinates. They use minutes and seconds, which is kind of awkward, but they would say it's like you guys, when you looked at using stellarium, you looked at the star coordinates, or the altitude of a star and the azimuth of a star. It would say something like 48 degrees and then 39 minutes. One line is a minute, and then 22 seconds. And then they could put a decimal. They might say 22.42 seconds if they want to get really precise. And 60 minutes, you would never see a 60 here, or a number bigger than 60, because then it would just be another degree, right? So if you said 48 degrees, 60 minutes, well, that could be correct, but that's ridiculous. You'd just say 49 degrees. So this number is always less than 60, and that number is always less than 60, because the number of seconds, there's also 60 seconds in a minute. So as soon as you get to 60 seconds, you add 1 to here. You get to 60 minutes, you add 1 to here. Okay, now what that means is, of course, that 1 arc second, and they call them arc seconds because it's a second of a degree of an angle of an arc, not of a time second. So these are arc seconds. So 1 arc second is 1/60th, right? 60 times smaller than an arc minute, and an arc minute is 60 times smaller than a degree. So 1 arc second is 1/3600th of a degree. So if you break up a degree into 3,600 parts, that's an arc second. That's tiny, right? You can imagine in geometry class when you're measuring angles, oh, I think it's 38 degrees or something. It's really hard using a protractor to get within 1 degree of the right answer. Can you imagine getting into 1/3600th of a degree? Breaking up a degree into 3,600 parts? I mean, so like here, like here's our angle, and here's maybe 1 degree, and that's even bigger than a degree. And imagine breaking up into 3,600 parts and telling which one it is. That's crazy. It's really hard. And people a long time ago couldn't do it. It's just too tiny. Now they could do to arc minutes, and that's pretty impressive too, right? Breaking that up into 60 parts. And that's what they had to do to get accurate enough data on the planets and stars and things to really start doing good astronomy. They had to make accurate measurements, and it wasn't until like the 1500s, 1600s where they could actually do that, and then they could really start doing things. Now this happened with Tycho Brahe and Johannes Kepler, who we'll talk about in a later chapter, and how they were able to use really good measurements to finally figure out really good scientific stuff about the planets and the solar system and everything. Okay, but just be aware of that, the minutes and seconds things. It'd be a lot easier if they just used decimals, but I don't know, historically, that's what they use, and they still do, so you should know how that works. And because they use it again for navigation on Earth too. If you look at charts, maps, and things, they typically use arc minutes and arc seconds. So you should know how that works. All right, I'm going to end this video now. Thank you for holding on this long, and I will see you in more videos. Goodbye.